Good afternoon, everyone. Today we are very happy to have Martin Sasieta from Madrid, although virtually, to give us a nice talk about holographic complexity of quantum black holes. So please take it away, Martin.
Okay, thank you very much, Longchen, and thank you to the rest of the organizers for inviting me to give you a seminar. So my talk is going to be based on this paper that appeared on the archive last month, and which was done with collaboration of Roberto Emparan, Antonia Francino, Maria Tomasevich, and myself. Okay. So the outline of my talk is going to be the following. I will start by introducing and motivating why it's important to talk about quantum corrections to holographic complexity. I will then introduce the setup of our work, which is the quantum BTC black hole. I will continue to talk about the holographic complexity of this type of black holes, and I will end up with some conclusions. Okay, so a lesson that we've learned in ADS-CFT is that space emerges from entanglement. In particular, there has to be a property of the entanglement structure of the state which captures the total amount of emergent space. So this property is believed to be some notion of complexity. The reason is that the interior space of a black hole grows linearly as the number of gates in a quantum circuit that prepares the time-evolved state. So you can think of the time-evolved thermofield double as being prepared by this quantum circuit, this tensor network, which consists of the asymptotic ADS regions, which represent the short-range entanglement structure of the state, together with a cylinder that glues together the two regions. And the complexity of such a state, when you apply the time evolution operator, it grows linearly, basically because the cylinder grows linearly in size. Okay. Apart from this heuristic this definition, there are in the continuum two holographic observables which are known to incorporate this linear growth. The first one is the volume complexity of the state, which is defined in terms of the volume of the extremal codimension 1 hypersurface, which is anchored to the asymptotic boundary of ADS. And this observable literally measures the amount of emergent space. So it has a nice, it's a nice observable from the point of view of the tensor network heuristics that I was talking about before. On the other hand, we have the action complexity of the state, which is given in terms of the on-shell action on a space-time region, which is called the Wheeler-DeWitt patch, and which is defined in terms of the causal domain of dependence of any slice that is anchored to the asymptotic boundary of ADS. And this observable, it also captures the linear growth of late times for black hole state. And it's quite remarkable that the precise slope that it produces, it's given in part by some contribution coming from the future singularity of the black hole. So even if this observable is an effective field theory observable in the gravitational side of things, it receives contributions from the future singularity. Okay, so these observables serve as definitions of the holographic complexity of the state for certain states in holographic systems in the large C limit. So for finite central charge or finite entropy, there must be also bulk quantum corrections to these quantities, coming from the fact that now the state of the bulk fields can backreact on the geometry, and also it's a proper quantum state. So in particular, there will be a contribution at this order coming from the complexity in preparing the bulk state. So we expect that for volume, the leading corrections are of this kind. So at leading order in the 1/c expansion, you would expect that this volume complexity observable is given precisely by its classical description, but then at order next to leading order in 1/c, you would expect contributions coming from terms such as the semi-classical backreaction of the state of the quantum fields in the bulk, also possible terms which would be Wald type terms coming from loops in the bulk. So this would correspond also to higher curvature terms. And then maybe the most important part of the complexity would be associated to the proper complexity of the bulk states. And well, the difference between the psi and phi states is that the psi is a full state in the UV exact quantum theory, so in the conformal field theory, whereas this phi state is just a semi-classical state of matter in the gravitational side. It's a state within the code subspace. So in this sense, these corrections for action complexity are less clear. And in fact, we will argue that at least in our setup, the action complexity proposal doesn't seem to have such an expansion. But the importance of studying such corrections is that this could serve to characterize the precise definitions of volume and action complexity from the point of view of the boundary, which would then serve to also give a characterization of the interior geometry and whether this geometry exists for general microstates of the black hole. Okay, so our motivation was that there is no precise definition of the bulk volume complexity and action complexity for weakly coupled fields. So the previous expression that I just wrote is just tautological. We don't know any definition for C bulk. So instead of trying to define these notions for a weakly coupled supergravity field, we were thinking to consider bulk theories in which gravity couples consistently to holographic conformal fields. And then one can use the doubly holographic description of the system to say something about these quantum corrections from classical quantities in the higher dimensional bulks. And in particular, there is a set of models which implements these doubly holographic perspectives in a very simple way. And these are the holographic brain wall models that I will introduce. So in a similar approach to study entanglement, these models have been useful to understand the island formula from the point of view of entanglement wedge complementarity. So the island formula, the island that forms in the interior of the black hole is really in the entanglement wedge of the radiation. And you can see this using a doubly holographic setup in which the island is literally connected geometrically to the radiation. Okay, so let me now talk and introduce the brain-walled holographic models that I will be using in this talk. So even if we're going to always treat these models from the point of view of the effective holographic descriptions in the bulk, it's very useful to keep in mind that in the UV, the definition of the system is in terms of a 2+1 dimensional conformal field theory on a spatial sphere, which is coupled to a conformal defect on the equator. So such a construction is called a defect CFT. Okay, so a defect CFT looks like this. You have a 3-dimensional conformal field theory, and then you couple it to a 2-dimensional conformal defect. And it will be useful for us to assign values of the central charges to each part of the system. So the 3-dimensional central charge is just, well, it can be read from the 2-point function of the energy momentum tensor, and it's C3. And the number of degrees of freedom of the defect, that's the central charge of the defect, is C2. So since we will just work with the effective holographic description, this description is only exactly valid when you take the limit of large central charge. Okay, so C2 and C3 are going to infinity. And it will be useful for us, I will explain why, to keep the ratio fixed between the two central charges, and actually for the ratio to be much smaller than 1. So basically the defect is the one that dominates the number of degrees of freedom of the system, and you can view the three-dimensional CFT as some sort of quantum correction to the unperturbed defect. Okay, so the first holographic description of the system, or the brane perspective, is to replace the defect by its dual ADS3 gravity. And so here in the picture, we have replaced the defect by a three-dimensional ADS3 gravity. And since the CFT couples to the defect, the CFT can also enter into the gravitational sector, and in fact, it enters as matter. So the CFT lives on both sides, on the rigid bath sector and also on the gravitational sector. And the way to couple these two sectors is through transparent boundary conditions in the asymptotic boundary of ADS3. Okay. So the effective action in the gravitational sector in this brane perspective is just Einstein gravity in 3 dimensions with negative cosmological constant and coupled to the matter CFT. And this theory is an effective field theory, so it would also have higher curvature terms entering at higher order in some coupling that I will now talk. And there is a length scale, this L, which gives, so its inverse gives the cutoff of the effective field theory. So this CFT is a cutoff CFT. Modes above the cutoff have already been integrated out, and modes below the cutoff belong to the matter sector of the theory. Okay. So the way to holographically define the two-dimensional central charge of the defect is just using the standard dictionary between the ratio of the three-dimensional ADS scale and the three-dimensional Newton constant. And this length scale that captures the cutoff of the effective field theory is just the renormalized Planck length of this theory. So basically, the CFT renormalizes the Planck length. So the bare Planck length, if you want, is G3, and the normalization of the Planck length induces this new length scale, which is enhanced by the three-dimensional central charge, and it serves as the cutoff of the gravitational theory. So this effective field theory will be a valid description whenever this renormalized Planck scale is much smaller than the ADS scale. And this equivalently imposes that the effective coupling that I was talking about, so the ratio between the three-dimensional central charge and the two-dimensional central charge is much smaller than 1. Okay. Also, this coupling, the effective coupling, controls the interaction of the CFT with gravity. The semi-classical backreaction of the CFT state is controlled precisely by the effective coupling. So it's proportional to the three-dimensional central charge and to the Newton constant. Okay. So there is a second holographic description of the system, which is in terms of a four-dimensional bulk with no holographic CFT on it. So the idea is that once you replace the holographic CFT in the previous description, you end up with this doubly holographic perspective, which consists of a four-dimensional ADS bulk with some brane, which is anchored to the hemisphere of the asymptotic boundary. So in this description, the effective action is just pure Einstein gravity coupled to a purely tensional brane. So pure Einstein gravity with negative cosmological constant, of course, coupled to a purely tensional brane. So the brane, which is anchored to the hemisphere of the asymptotic boundary, is just a purely tensional brane. Okay? And also, the effective action in the previous description, so the gravitational action in the brain, is just induced from this 4-dimensional gravity on the brain. So once you use the renormalization, the holographic renormalization procedure on this brain without adding extra counter terms, what you get is that there is a normalizable graviton mode, which is localized onto this brain, so that gravity in this 4-dimensional picture is also approximated by a 3-dimensional gravitational theory in the brain. And this is precisely the previous description that I was talking about. So the 4D Newton constant relates to the 3D by this equation. So the 4D has dimensions of, 4D Newton constant has dimensions of area, the 3D has this dimensions of length. They're related by the 4D ADS scale, and the 4D ADS scale relates to the 3D ADS scale by precisely this equation. Okay. So these two expressions allow to define holographically the 3-dimensional central charge using the standard dictionary. So it's L4 squared divided by G4. Okay. Any questions at this point? Okay. So now that I've introduced the system, I will introduce the state that we will be analyzing. So this state is just the quantum BTC black hole, which was well initially studied in these two papers, and it was revived and studied further in this last paper by Roberto, Antonia, and Benson Wei. So the idea is that you can define a thermal state of this defect CFT system holographically from a solution of a black hole localized onto the brain in this ADS4 bulk. So this solution is called the ADS4 symmetric, and it has this form. So the metric, it's conformal to a more standard black hole metric that you can imagine. The conformal factor will be important later, but the idea is that the T and R directions are orthogonal to the internal sphere, to the metric on the internal sphere, and the redshift factor of the black hole, or the blackening factor, is just given by these standard terms in ADS4 with the Newtonian potential in 4 dimensions. Okay, so this mu parameter just depends on the mass of the black hole, whereas L depends on this effective coupling that I was talking about. So L is just from the brain perspective, is the scale of the effective field theory, and it controls the quantum corrections of the CFT. It's proportional to the effective coupling. So L over L3 is the effective coupling. And also in this 4D picture, this L controls the inverse tension of the brain. So taking the effective coupling to be very small is equivalent to taking the brain very close to the asymptotic boundary of ADS. And this is the regime of parameters that we want to study for the brain perspective to make sense. So in these coordinates, the brain lies at x equals 0. So x is just a polar angle along the sphere. The metric on the sphere is not the round sphere. This metric is not spherical symmetric. But x equals 0 is just, you can think of it as the equator of the sphere, and it's precisely where the brain lies at. So the rigid buff, on the other hand, lies at the rigid asymptotic boundary of this ADS4. Okay. So from the brain perspective, the previous solution induces a state which is described by a quantum BTC black hole. So this quantum BTC black hole solves Einstein's equations sourced by the holographic stress tensor of the CFT. In particular, the induced metric looks pretty much like the BTC metric, with this correction coming from the 4D Newton potential. Okay, so in 3D, this correction is in principle not expected from any Newtonian analysis, but its origin is just the 4D Newton potential. And this metric solves Einstein's equations sourced by stress energy tensor, which is traceless and in order, and then it's proportional to the three-dimensional central charge and to this mu parameter, which is controlled by the mass of the solution. So the full solution, the full quantum BTC solution, has two parameters. The first one is defective coupling, which controls the position of the brain, and this fixes the theory that you're working with. And the second one is just the mass of the solution. And it's peculiar that the mass is upper bounded by some value, and this is related to the fact that at some point when the black hole is large enough, it doesn't fit between the brain and the asymptotic boundary in the four-dimensional description. Okay. Also, there is a way to analyze a different state of the system, which consists of a small black hole in ADS3. And this new solution is just obtained by taking the quantum BTC metric and replacing +1 where this -1 is at. Okay, this new solution has the interpretation of a small black hole in ADS3, which is generated by quantum backreaction of the CFT on the brain, and its classical description is just horizonless. It's just it's just a conical defect in ADS3. So once you put the matter CFT on top of the conical defect, it generates a horizon, and it gives you this new solution, which looks like a small black hole in ADS3. Okay. So any questions?
Yes, actually, I have a question. So when you show this metric, it's already the back-reacted metric. Is that correct, or the picture you showed is the back-reacted one, like?
Yeah. So this metric is back-reacted by the stress energy tensor of the matter CFT on the brain. And basically the back reaction, what it does, it changes the redshift factor. It adds this extra factor to the BTC metric.
Okay, so but L, when L goes to infinity, that means there is no, like the brain tension will become 0, right?
Yeah, exactly. From the brain perspective, that limit is not realistic, because in the brain description, this L is giving you the length scale of the effective field theory. So when you take L to infinity, this would mean that the regime of validity of the effective field theory is so the cutoff becomes much larger than the EDS scale, and therefore this solution doesn't make sense. So in other words, if you think in the four-dimensional perspective, when the brain is very close to the boundary, the 4D gravity is localized onto the brain approximately, and this is what gives you the effective gravitational theory of the brain. But if you take the tensionless limit of the brain, then the brain is in the middle of ADS and actually disappears. So in that description, gravity is no longer three-dimensional. You just have a 4D gravitational description. You don't have a brain description.
Okay. But even in the tensionless limit, there are still gravitational modes that I suppose I should go from, say, one foliation to the other foliation, like the transverse modes. But maybe it's unrelated here.
So I think that the main point is that the normalizable graviton state, which is bounded to the brain, when you take the brain to be tensionless, it's no longer bounded to the brain. It's just a 4D graviton mode.
Okay, thanks.
Okay, so Okay, let me now show you how powerful this holographic construction is. So the first thing that was actually computed in this paper is the thermodynamic entropy of the quantum BTC state. So from the Rita-Carnegie formula in the 4D bulk, this thermodynamic entropy is just given by the area of the four-dimensional black hole. Okay, so this thermodynamic entropy, which I've called here generalized entropy for reasons that I will explain in a moment, is just the area of the 4D black hole in units of the 4D Planck scale. So this quantity from the brain perspective admits the interpretation of a generalized entropy with a term which represents the entanglement entropy of the CFT state across the horizon. So when you expand this four-dimensional area term in terms of the 3D, so for a small effective coupling, the leading term is just the three-dimensional Bekenstein-Hawking term on the brain, but then you have corrections, okay? And the correction, which is linear in this coupling, is interpreted as the entanglement entropy of the CFT state across the horizon. So from the brain perspective, the previous definition, which was just classical in the 4D bulk, admits the interpretation of a generalized entropy in the 3D in the brain description. So this generalized entropy satisfies the laws of thermodynamics. This was shown in this paper from the point of view of the brain perspective. So when you change the mass of the solution, the change in mass is associated to the temperature of the black hole times the change in the generalized entropy, and this was in fact proven to all orders in the effective coupling on the brain. And the second law on this quantity basically follows from the second law of the area term in the 4D bulk. Okay, so let's now talk about holographic complexity of this type of black holes. So to talk about holographic complexity strictly, we need to consider the purification of two copies of the defect CFT system that describes the two-sided black hole. So the volume complexity and action complexity of this state will be given in terms of the standard prescriptions in the doubly holographic bulk. And the reason is that you can view the brain as some thin layer of matter in the ADS4 bulk, well, the complexity of this state will be just given by the standard prescriptions. So the brain doesn't alter the prescriptions. So the volume complexity will be just given in terms of volume of a three-dimensional slice, which is anchored to the two asymptotic boundaries, because now we are considering the two-sided black hole. And the action will be just given by the on-shell action evaluated on the four-dimensional Wheeler-DeWitt patch that lives in the doubly holographic perspective. So from the brain perspective, we expect that these definitions should include the quantum corrections to holographic complexity coming from the state of the conformal field theory on the brain. And this is one thing that we will check. And in fact, we will show that volume complexity admits such an expansion, whereas action complexity does not seem to admit such an expansion. Also, since the effective number of degrees of freedom of the quantum BTC black hole receives corrections from the bulk entanglement entropy, we were thinking of testing the late time growth of these proposals of the generalized complexities with the corrected slope that we would expect in a quantum circuit. So the thermodynamic entropy is giving an idea of the approximate number of degrees of freedom of this black hole and receives corrections from the entanglement entropy of the quantum field theory. and the expected slope for the growth of complexity will also get correct in this sense. Okay, so let's start with volume complexity. So the extremal volume slice is the Einstein-Rosen bridge is a cylinder. Topologically is S2 times the transverse direction to the spheres. But the metric is not spherically symmetric, and in fact, the brain cuts the sphere for some particular value of the polar angle. Okay? So you can view the Einstein-Rosen bridge cut by the brain orthogonally along the spheres. And the complexity of this of the quantum BTC state will be just given by the volume of this two-sided object. In particular, since the ADS4 symmetric lacks of spherical symmetry, it is difficult to extremize and find the exact Einstein-Rosen bridge exactly, analytically. So what we did in the paper was to expand the volume complexity functional in a power series in this effective coupling. So this means just expanding the extremization problem in the effective coupling and extremizing order by order in the effective coupling. So to leading order, this means taking the effective coupling to 0. Remember that this is just getting rid of the three-dimensional CFT and just staying with the defect description, which from the brain perspective gives you the BTC black hole. So in this limit, the brain is exactly placed in the asymptotic boundary of the ADS4 bulk. And from the properties of the hyperbolic geometry, the volume, the three-dimensional volume which lives in the 4D bulk, is dominated by its intersection with the brain. So the volume of sigma, of big sigma, will be given in this limit exactly by the ADS4 length scale times the volume of small sigma, of the intersection with the brain. And also the semi-classical backreaction on the brain disappears completely in this limit. And what you get is the redshift factor of the BTC black hole. So the leading order extremization problem will be just to find the extremal intersection with the brain, which lives in the BTC geometry and which extremizes its volume of the brain. So this is basically saying that the classical limit of this generalized notion of volume complexity will be precisely given by the volume complexity of the BTC black hole. Okay? This is what we showed in this limit. So in the ultraviolet description in this limit, the system is described by a pair of two-dimensional CFTs, which are not defects anymore, and which are in the thermophile double state, describing a BTC black hole. So this notion of generalized volume complexity correctly reproduces the classical limit. Okay, so to linear order in the effective coupling, to next to leading order in the effective coupling, there are two effects that one needs to take into account in order to extremize this big sigma in the 4D bulk. The first one is the semi-classical backreaction of the CFT on the brain. And the second one is related to the first correction coming from the normal derivative of this of the volume of small sigma in a direction orthogonal to the brain. Okay? So if you want, you can think of the leading term as the leading term in a Pfefferman-Graham expansion, which is just the volume of sigma, whereas the next to leading term is just proportional to the normal derivative of this volume on sigma, on small sigma. So the first effect is just the fact that now the redshift factor gets a correction coming from the backreaction of the CFT, whereas the second effect is just the fact that you can expand a la Pfefferman-Graham the volume of sigma and get that the leading term is just the volume of small sigma plus some corrections that depend on the normal derivative of the volume of small sigma. Now, the normal derivative of the volume of small sigma will vanish because the extremal slice, extremal volume slice, is set to symmetric across the brane. So this effectively imposes Neumann boundary conditions on the brane, and this means that the leading order correction coming from the Pfefferman-Graham expansion of the volume will vanish. So at this order in defective coupling, there is also a time-independent UV divergent contribution to the complexity coming from the Pfefferman-Graham expansion on the rigid asymptotic boundary of ABS. But we won't analyze this contribution in much detail. Okay. So to sum up, we have found that the generalized volume complexity of the quantum BTC black hole admits an expansion in the effective coupling of the brane. And the classical term is just the volume complexity of the two-dimensional defect, which is the volume complexity of the BTC black hole. And these two terms form the leading quantum correction that we were expecting. So the first one is just time independent. It corresponds to the complexity of the short range correlations of the bath. And the second one is time dependent, and it corresponds to the semi-classical backreaction of the state of the conformal field theory on the brane. So to sum up, the CFT on the brane has two contributions to this formula. The first one is that modes which live above the cutoff that don't enter in the effective field theory just renormalize the Newton constant, and modes below the cutoff contribute through the semi-classical backreaction on the extremal volume on the BTC black hole. Okay, and in particular, something which is surprising from this analysis is that there is no complexity associated to the bulk state at leading order in the effective coupling. So we didn't find any non-zero contribution which is associated to the complexity of the bulk state. And the origin of the vanishing of this complexity of the bulk state is just that the normal derivative to the extremal slice in the bulk is zero. So we expect that this property is true in more general induced brane world models. So whenever the brane on the bulk is purely tensional, then the extremal slice will intersect it orthogonally. And then we don't expect that the leading Pfefferman-Graham corrections will enter into the quantum correction. So we don't expect any term which is associated to the complexity of the bulk state. So now that we know the quantum corrected volume complexity formula, we can analyze its late time regime. And what we got is that the quantum BTC black hole computes volume complexity faster than the respective BTC black hole of the same mass. So what we got is that at late times, the rate of volume complexity is given by 2m, which is the result for a BTC black hole of mass m. And then you get some correction, which is proportional to this effective coupling. And this function that just depends on the mass of the solution is always positive. So the rate of growth is slightly larger than the rate of growth of the BTC black hole. And well, this result was expected because when you expand T times S-gen as a function, as a power series in the effective coupling, you get a similar expression. So the leading order term is just 2 times the mass, which would correspond to the SMAR relation in the absence of three-dimensional CFT. But then you get some corrections coming from the three-dimensional CFT, and the functions that you get do not precisely match, but quantitatively up to order 1 numbers they agree. So let me just show you this result in a plot. So here I've plotted the rate of volume complexity growth as a function of mass. So the QBTC black hole is just the range of positive masses of this solution. And you see that the rate of complexity growth quantitatively agrees with the with expected slope, which is t times sgen, and it's slightly larger than the t times s of the BTC black hole. So the quantum BTC black hole, due to the quantum corrections to the volume complexity proposal, computes slightly faster than the BTC. So also for the negative, so for the branch of negative masses, these these solutions were just these small ADS3 black holes, which came from semi-classical backreaction of CFT on top of a conical defect. These solutions, you see that they compute at a rate which is slower than t times sgen. And the reason is that this t times s in 3 dimensions, so the smart relation for small black holes in 3 dimensions doesn't depend on the Schwarzschild radius. So the temperature of a small black hole is inversely proportional to the radius, and the entropy is proportional to the radius, and then the product of the two, so the t times sgen, that is independent on the Schwarzschild radius of the black hole. And these small black holes, the Schwarzschild radii is proportional to the effective coupling of the CFT, basically because they are created from semi-classical backreaction. So the rate of growth of volume is a quantum effect, whereas t times sgen in 3 dimensions, particular 3-dimensional scaling of things, it's independent of the effective coupling. And in particular, when you take the classical limit of these solutions, they become horizonless, they just become conical defects in ADS3, and they do not compute. So the space-time is static, everything is constant in time, whereas this t times sgen just remains there. Okay, any questions?
Yeah, I have
Okay.
a question.
So let me continue.
Sorry.
Yeah.
I have a question on your plot. So it looks that it is double valued in the positive mass region for the growth rate of the volume complexity. So that means 2m is not necessarily dominant, like the leading contribution.
No, this is related to the fact that in the quantum BTC solution, there are different branches. So you can have 2 different types of solution with the same mass. Okay, so the parameters on the metric look different, but the mass of the solution is the same. For example, the ones that we will be interested in are just small corrections of a BTC black hole, and these are the ones which correspond to this branch. But then the second branch, which is the one coming here, corresponds to a large correction to a BTC black hole. So it doesn't behave as a BTC black hole. So in particular, the state of the CFT on top of the BTC looks thermal for this branch, whereas for the other branch looks Casimir dominated. So the energy momentum tensor looks different.
Okay, but just to make sure I understand, the result you showed before this slide is it's only for the branch that has the BTC black hole-like behavior.
Like no, it's for both of the branches. Yeah, but the interpretation, the correct interpretation, if you want to think of the QBTC as a small modification of the BTC due to quantum effects, it is just for the branch, for the first branch. It's just for this branch, yeah.
Okay, I see. But in this case, how do you distinguish between like the term? Okay, because you have showed some terms that I think it's probably, you mean dominant contributions, and the dotted terms are not like they are subleading in terms, maybe in terms of G effective. But it looks like even for the first 2 terms, it's hard to tell like which is more dominant for a given mass. Then how can you like be sure that the terms that you neglected will be subleading?
Okay, so you're saying that the F1 can be comparable to 1?
Right.
But then it's parametrically suppressed by the effective coupling on the brain. So you can take this effective coupling to be 10 to the minus 20, and then you can always make it smaller than 1. The point is that it's parametrically suppressed. It's a quantum correction which is parametrically suppressed, if you want, in H bar on the brain, which is controlled by this effective coupling.
I see. Probably because in this plot you didn't take this G effective to be small enough, so that these two branches are quite separated from each other.
Oh yeah. Okay. You're talking about the difference between F1 and F2. Okay.
No. I'm talking about, say, a single black curve.
Yeah.
Right, because for the same value of m, then it goes back, right?
So you're talking, okay, so you're talking about this black curve that gives you the exact rate of volume?
Right, right. It gives you, like, it's double valued horizontally, vertically, sorry.
Okay. I know what you mean. Okay, so yeah, exactly. So for the second branch of black holes, it's not exactly true that you get this sort of expression, and the reason is that this expansion in the effective coupling might not make sense. So this expansion, even if it formally is true for any term, in this branch it can be true that that the effective coupling is not small to describe this branch. Okay, so if you are thinking just about a quantum BTC black hole as a small correction of the BTC, we are expanding in this region, and there this expansion makes sense.
Okay, thanks. Okay.
Maybe I can add one thing. I mean, the limit where, so this plot that Martin is showing here, it's a plot, as you said, for a finite value of the G effective. But if you send a G effective, you make it very small. These curves, I mean, the black curve goes first almost flat and then goes up just above the one for the second branch.
Yeah, like the black curve will be squeezed somehow. Exactly.
I think that this, I mean, you have to take into account this when you're, so in that sense, even if...
I was actually thinking that way, because when you plot, maybe doing this numerics, you didn't really take the G effective to be small enough so that they are quite...
Yes. Exactly. Yeah, we didn't take it to be infinitesimal.
I see.
Because otherwise it would be yes. Sorry, thank you.
Thanks.
Yeah, we actually took it 1 quarter to be 1 quarter in this plot. So yeah, as what Roberto was saying, when you take the effective to 0, these two branches just merge on the BTC line, basically, very close to the BTC line. So this point becomes very close to 0. Okay. So let's now talk about action complexity. So the Wheeler-DeWitt patch in the 4D bulk will be complicated because the metric is not spherically symmetric, and in general caustics will form. But from the properties of the symmetric, it is possible to find two causal diamonds. This means some space-time region in which the time and radial part factors out from the internal sphere, which delimit the Wheeler-DeWitt patch. So the real Wheeler-DeWitt patch will lie in between the green causal diamond and the red causal diamond in the bulk. And well, this doesn't represent a Penrose diagram, it just represents a constant section of the geometry. The internal manifold doesn't really factorize in the symmetry. because of the conformal factor. But the idea is that the real Wheeler-DeWitt patch will lie in between these two regions. And we were able to show in the paper that both causal diamonds have the same late time growth of action. And therefore, the real Wheeler-DeWitt patch will also have the same late time growth of action. And so we don't need to really, we are not interested, or we are not precise enough to talk about the value of the action. We can just focus on the late time growth and focus on the red diamond, which looks like the infrared, looks like adding some infrared regulator in the back. Okay, so this would be the complexity of the full state will be a UV part, which depends on the asymptotic region, plus the action evaluated on this regulated Wheeler-DeWitt patch. And we take the prescription of taking the null and joint terms in such a way that the full action is additive. And we don't want to focus on the exact value because we don't know how to compute this UV piece, but we just will just stay. So we'll just talk about the late time growth. So the first term that contributes to the late time growth is the bulk contribution in the 4D Wheeler-DeWitt patch, and this term just consists of two different terms. The first one is the Einstein-Hilbert term of the 4-dimensional Wheeler-DeWitt patch, and the second one is the value of the brain action on the intersection of the 4D Wheeler-DeWitt patch with the brain. So the intersection of the 4D Wheeler-DeWitt patch with the brain is just the 3-dimensional Wheeler-DeWitt patch that you would draw in the brain. And these terms are easy to compute because the solution is locally a vacuum solution, and therefore the first term is proportional to the volume of the 4D Wheeler-DeWitt patch, whereas the second term is proportional to the volume of the 3D Wheeler-DeWitt patch. And the volume of these space-time regions is easy to compute. Okay, the second type of term that contributes to the action comes from codimension 1 boundaries of the Wheeler-DeWitt patch. And among these, the only one which is relevant for time evolution comes from the future singularity of the black hole. So it's the Gibbons-Hawking-York term in the future singularity. In particular, we computed that the time derivative of this Gibbons-Hawking-York term coming from the future singularity is constant. And this is because the Wheeler-DeWitt patch intersects the amount of future singularity intersected by the Wheeler-DeWitt patch grows linearly in time with a constant slope. So the constant slope is just a function of the mass of the solution and doesn't depend on the effective coupling of the CFT on the brain. And this is, well, this already shows some problems arising in the action complexity proposal, which is that if you assume that the generalized action admits an expansion in the effective coupling, then the late time growth has to also admit the same expansion. And this term is already saying you that that might not be true for action, and in particular, this term doesn't admit an expansion in the effective coupling. So all the terms in the power series in the effective coupling, except for the 0th order term, vanish. So the last type of term which contributes to the late time growth comes from the joint terms. So these are basically arising from the intersection of codimension 1 boundaries of the Wheeler-DeWitt patch. And among all of these blue joint terms that you would have, the only one which contributes to the late time growth is the one coming from the lower tip of the Wheeler-DeWitt patch. So the time derivative of the value of the action on the joint is given at late times by twice the temperature times the generalized entropy. Exactly. So this term, for example, it admits an expansion in the effective coupling. Okay. There is an extra type of joint terms which arise from the non-smooth intersection of the Wheeler-DeWitt patch with the between the Wheeler-DeWitt patch and the brain. Okay, and nonetheless, this intersection is smooth enough so that the joint terms values. So the normals to these codimension one boundaries of the Wheeler-DeWitt patch become tangent to the brane at the intersection. And then because tangent properties of space-time become are continuous, the normal to this hypersurface is continuous across the brane. And this means that the intersection is one-time differentiable across the brane. And for those type of intersections, you don't have any new joint terms appearing in the game. So we have seen that the different terms in the action behaves in a different way. In particular, the bulk and joint terms admit an expansion in the effective coupling, but the Gibbons-Hawking term doesn't. The surprising thing is that when you add the three together, the final result is a slope which is independent of the effective coupling. And therefore, the late time value of the action complexity doesn't admit an expansion in this parameter. And this calculation, contrary to what happened for volume, is exact to all orders in the effective coupling. So the precise value for the late time slope is just the value for the BTC black hole, which is proportional to the mass, times some function that depends on the mass of the solution. So remember that this is a different expansion to the one for volume. In the one for volume, we were expanding in the effective coupling, and we were finding the next two leading order terms. Whereas here, what I'm saying is that all the terms when you expand on the effective coupling are zero, and the leading term, so except for the leading term, which is of the order G effective to the zero, and this term gives you this function of the mass. Okay, this is already problematic if we want to assume that the generalized action complexity admits an expansion, a quantum expansion of the brane. So, moreover, this particular value doesn't reproduce the value of action complexity for our BTC black hole. And in particular, when you take the limit G effective going to zero, this value is unaltered. So you would still get the same value for the late time growth of action complexity, which doesn't reproduce known results. So it should reproduce the value for the BTC black hole if the generalized action was a consistent quantum expansion of the brane. Okay. So these two results suggest that at least this notion of generalized action doesn't admit a consistent quantum expansion as opposed to volume. So from the point of view of the four-dimensional bulk, this is an effect. So the late time slope of action complexity is independent of the tension of the brane. So the effective coupling controls the inverse tension of the brane. When we take it to be very small, when we take the effective coupling to be very small, the brane is just very close to the asymptotic boundary. On the other hand, when we take the effective coupling to be of order 1, the brane is sitting in the middle of ADS4. And we have just shown that the late time growth of action complexity is independent of the tension of the brane. So it would give the same result in these two computations. And in particular, we can formally take the limit G effective going to infinity, even if this doesn't make any sense from the point of view of the effective theory in the brane. And we can interpret the value that we got for the late time growth of action as the one associated to the Schwarzschild ADS for hyperbolic black hole that you get in this limit. So if you take this limit of the C metric, the bulk metric that you get is the one of a Schwarzschild ADS for black hole. And then you can reproduce the value that we got for the action complexity just by taking the formal limit. So the function of the mass that I was referring to here corresponds just to the ADM mass of this Schwarzschild ADS for black hole. Okay, so in other words, we found that the tension of the brane is a flat direction of the time-dependent part of the gravitational action in the Wheeler-DeWitt patch. And this property was already known at the level of the value of action complexity for the ground state of a defect CFT. So in this paper, they show that for the ground state of a defect CFT, so in empty ADS, the exact value of the action with all the UV divergences is independent of the position of the brane. Also, for smoother interfaces like the Janus ADS solution, action and volume also start to behave similarly again. So it's probably a property of this very thin type of interfaces that we're studying. And in the cases of smoother interfaces, there is not, so the interpretation of the gravitational induced theory on the brane is not available anymore. Okay? So in conclusion, let me just wrap up. We have analyzed the volume complexity and action complexity prescriptions for the quantum BTC black hole, which holographically include the large central charge quantum corrections of the bulk conformal field theory on the brane. We have found that the volume admits a consistent expansion in the bulk effective coupling of the CFT. And we have also found that in induced gravity scenarios, so when the brane is purely tensional, the bulk complexity of the quantum fields on the brane vanishes at leading order in defective coupling. So we have also found that the contribution from the bulk CFT to the late time growth agrees quantitatively with T times S-gen. So the CFT adds computational power to the black hole, as we were expecting. And also we were able to study the volume complexity of these quantum dress conical defects, which do not compute classically. And we show that their rate of complexity growth is suppressed with respect to T times S-gen. So for action complexity, we found that the value of the late time slope is independent of the effective coupling, and that it doesn't give the action complexity rate of the BTC black hole. Therefore, the generalized action complexity doesn't reduce to the 3D action complexity plus quantum corrections. More generally, in any holographic complexity proposal, which has a purely geometric character, like volume complexity, possible generalizations of volume complexity, or space-time volume, the generalized proposals, at least in our setup, they will admit an expansion in the effective coupling as a consequence of the properties of hyperbolic space. So when you take this effective coupling to be very small, at leading order, these geometric quantities will be dominated by the intersection with the brane. This will give you the classical terms for these quantities, and then the quantum corrections, which are linear in this effective coupling, will come from different terms, depending on the proposal. So lastly, it would be interesting to see whether this behavior for action complexity persists in more general brane-well models, like those in which the action of the brane in the bulk has an explicit DGP term, or whether this behavior is a peculiarity of our model. So that's it.
Thanks for the very nice talk, Martin. I think now we can take some questions.
Excuse me, I have a question.
Go ahead.
Yeah.
Just want to know the generalized entropy makes sense because the entropy of the black hole can be thought as the thermal entropy, but the holographic complexity of the black hole is the volume of the volume. So the generalized complexity. Why the complexity of the black hole? Or what's the meaning of the complexity of the black hole? Is that why it can add with the state of the complexity of the state? I think why it is makes sense. So it's my question.
Okay, so I think you're asking about the definition of what the complexity. So the UV interpretation of what we're computing. So in the UV, the state that we are considering is just the state of two defect CFTs which are not coupled together, but which are entangled in the thermofield double state, and we are computing the complexity in creating this thermofield double, and in particular, when you use the left plus right Hamiltonian to time evolve, we are computing how fast this complexity grows.
Okay.
So
yes, we can think about this question in the holography, but the generalized entropy of the black hole has the thermal entropy. The thermal entropy of the black hole is will count the microstate of the black hole. Whether the complexity of the black hole means the some state of black hole and the complexity of this state.
yes, so the generalized entropy is a property of the thermal state. It's just counting the number of states, as you said. But the complexity, how complexity grows, is not just a property of the state, it's a property of the Hamiltonian. So by computing the latent growth of complexity, we are talking about some particular Hamiltonian of these two defect CFTs.
That's right, but the complexity can be defined for the state, such as the reference state and the target state. Well, the general entropy of the black hole, the thermal entropy is the thermodynamics prospect for a particular black hole state. In fact, we know that a black hole is in a particular state. So this particular state will have the complexity for the quantum theory. So is that complexity will, I think this complexity can be added with the complexity of the CFT state. The volume of the wormhole is not something can add with the complexity, with the quantum circuit complexity.
So are you asking about the precise characterization of what we're doing in the boundary? Because that's an open problem. So you can argue that volume and action behave similarly to a circuit complexity, heuristically, but at the moment, at least as far as I know, there is no precise definitions in the CFT of what volume and action are. But nevertheless, we in our paper we didn't focus on the precise characterizations, but we were just stating some properties that these proposals would have in these holographic brain wall models. In particular, we were able to give a phenomenological input for the quantum correction by using W holographic setup. But I agree with you that complexity, so it's not literally circuit complexity probably, and it is still an open problem.
Okay, thank you very much.
Thank you.
Anyone else would like to ask a question?
So I have a question, but maybe even a few. So thanks, Martin, for a talk. So based on your studies of action complexity, can you make already a statement about the behavior of the complexity equals volume 2.0? in this setup of interest?
Yeah.
So how does it behave?
Since that proposal complexity equals volume 2.0 is geometrical, because in that proposal complexity is given by the volume of the Wheeler-DeWitt patch, space-time volume of the Wheeler-DeWitt patch. Then this space-time volume at leading order, when you take the brane very close to the boundary, it will be given by the volume of the intersection of this Wheeler-DeWitt patch with the brane, which is the Wheeler-DeWitt patch in the three-dimensional theory. So it will have the correct classical limit, and then the leading quantum correction will also appear there, and well, it will be different from the one for volume complexity, but it will be there also. And any notion of complexity which is purely geometrical. Yeah.
So would it also have like this feature that the matter contribution to complexity at the leading order of the coupling is 0, or not? So you had like this
I don't
feature
think so.
for the okay. So okay, can you remind me, like in your action considerations, was it also the case that the matter contribution was giving a non-zero answer?
So in the action, we didn't even have an expansion of the quantum correction. So so in that case, it's much more drastic than that. So any geometric proposal will satisfy that it will have an expansion in this parameter. The action doesn't even have an expansion.
Oh, I see.
But other proposals will have different values for the quantum corrections. Like, for instance, if you change the notion of volume complexity by a different generalization, like you're extremizing over a different functional, then the leading quantum correction will be there, and you will have a complexity associated to the quantum fields at leading order. Yeah.
Good. So my other question would be, I mean, recently, you mentioned this in your summary in your talk, that there's been this more radical proposal that complexity equals to anything, in a sense that there are many covariant notions in the bulk that give rise to a linear growth and switchback effect. So if you apply it to your setup for codimensional one objects, is it obvious that, I mean, maybe it's obvious to you, is it obvious that if you look at, say, 4 versus 3D perspective, that it is the same leading order notion in both cases, defined in the same way by optimizing, say, the same functional?
No, it's not. It's not obvious.
Okay,
that's true. Yeah,
but it is the case for the volume, and it is the case for complexity equals to volume 2.0, 2.0.
Yeah. Because in those cases, you're computing just volumes of things, and then you can have Pfefferman-Graham expansions of everything, and the volume reduces just to the volume on the brane. So the volume reduces to the area of the brane. The space-time volume reduces to some three-dimensional volume on the brane, which is a space-time volume also. But this depends ultimately on the volume functional that you are doing the Pfefferman-Graham expansion in. So if you start with a different functional, which, for example, has terms which are proportional to the extrinsic curvature, then you're not guaranteed that this will reduce to a three-dimensional extrinsic curvature.
I see. Okay. So in this sense, like, these volume functionals are special, or seem to be special.
Yeah.
Okay. And can you? It also, I mean, it's just my ignorance, and I'm sorry about it, about the setup itself. So can you pursue this expansion to arbitrary high order, or like you have to? There's some fundamental reason that you have to stop at the next leading order.
No, you can do that in the setup, and the problem is that higher curvature terms enter in the effective action at order G effective square, and then when you are trying to analyze the quantum corrections to complexity, you wouldn't know which terms come from higher curvature corrections or proper quantum complexity of the bulk state. So, yeah.
Yeah. So the last question. So when you look at any of the complexity proposals, I mean, in most cases, I think in all the cases apart from one that comes to my mind, the result that you're gonna get is UV divergence. That is like this is the divergence associated with the volume of ADS, basically the standard UV divergence in holography. So when you look at the quantum correction to complexity proposals in your framework, this quantum correction, if it's non-zero, like, is it also UV divergent or it comes out finite?
Yeah, it's UV divergent also. Well, there is a UV divergence associated to the bath, to the rigid bath. And this is precisely associated to the infrared divergence in the bulk that you are talking about, in the limit of that you're close to the asymptotic boundary. But then the proper contribution to the complexity on the effective theory on the brain is finite. And well, the way to interpret this is that on the effective theory on the brain, the UV divergences have been absorbed in the renormalized Newton constant by the CFT, and therefore there is not any extra UV divergence that you should, in principle, be worried about. And yeah, the results that you get on the brain are finite.
So when you think about complexity in the, so I mean I'm not sure if this is correct, right? But like if you think about, I mean, actually maybe disappeared in your equations. So if you think about quantum generalizations of entanglement entropy, right? Like then you have, say, Ryuta-Kuyanagi, and then like you get correction that you interpret as a entanglement through the Ryuta-Kuyanagi of the bulk quantum field, coupled to gravitational theory. So if the complexity of the matter fields that are coupled to gravity comes out finite, my question would be like, what does it teach us about the reference state that one considers? So, the narrative typically was that like you get in complexity, you get the divergence because the reference state was taken to have a vastly different entanglement structure than, say, the vacuum of your quantum field theory. In particular, it might have been a special disentangled state. Whereas when you get the finite complexity, that typically means that you only alter your state with respect to the vacuum of a given theory in the infrared, like, and in the UV, like the state looks basically indistinguishable from the vacuum. So is there some, I mean, can one pursue like this framework in this direction to get something useful?
So okay, comparing these results with the entanglement entropy, what I would say is that when you have a bulk entanglement entropy, you also get UV divergences. This is what you were saying. But in principle, everyone expects that you can reabsorb these UV divergences on the Newton constant renormalization in the Ryuta-Kuyanagi classical term, in the area term. Okay, so the finite generalized entropy is UV finite. You don't have any UV divergences there. So for complexity, these notions of quantum corrected versions already incorporate that renormalization. So the classical term gets renormalized by the loops of matter of the CFT. And in principle, the full expression is a renormalized expression. So it's true that naively, the bulk complexity, depending on what reference state you choose, it will diverge because you would need to implement an infinite amount of gates. But then this notion, which is defined holographically from the point of view of the 4D perspective, is already renormalized. That's the power of this construction. So the sum of two terms given by the classical one plus the quantum correction is already finite.
I'm asking this because in the context of mapping between boundary complexity defined in boundary, I mean, in a CFT and complexity notions being holographic complexity proposal or something else, like the only case where so far we have a tremendous control is a case in which we consider states obtained by acting with stress tensor, exponences of stress tensor operators in the vacuum in, say, two-dimensional CFT. So these are, I mean, like this is due to work that Javier Magan and Paul Zaputa had and subsequent developments. So I'm just wondering if such states, if you can put matter fields in such a state when these matter fields are represented by a two-dimensional CFT in your setup.
I don't think so, because the boundary CFT is three-dimensional.
That's fine. I mean,
CFT.
Yeah.
So you could.
But can you think about like a two-dimensional analog of the setup? You can, I guess, right? I mean, is there something fundamental about dimensionality here?
Well, the only thing fundamental is that we have a solution about it. And, yeah, in other dimensions we don't have such solutions, and we will need numerics to solve everything. And well, this was a really interesting exercise because you were able to see everything explicitly and analytically.
Sure.
But yeah, I don't think there would be a problem, at least to do everything numerically. If one first tries to solve Einstein's equations of a black hole localized to a brane in ABS3. But
yeah, I mean, I don't think that it needs to be numerical. Probably it can be done analytically, but there's issues to these constructions between 3D and 2D that one has to deal with. If you want to induce gravity, then you have to see what kind of gravity you induce. If you just put a tensional brane, what you get naively is a Liouville gravity, which is not enough. You have to modify the construction in some way, and it's not entirely clear. But I think it might be possible to do something like what you say. I mean, I'm not sure how far one can take it, but it may be.
I feel like from this perspective, I would be probably more interested in, or maybe that's just arrogant to say, but I would be more interested in the complexity of the field theory.
Yeah.
So like this correction rather than like what comes out from gravity. The reason being that this is the bit that we understand in field theory in the setup that I mentioned. So maybe I would not be that worried about like what the gravity theory is, but rather what the correction is. Maybe that's too ignorant. Maybe I'm missing something. But
right. Yeah.
I think that I mean that could be interesting to do.
Yeah, and since it's in low enough dimensions, maybe one can do quite a number of things analytically. Yeah, whether you get something that's sufficiently non-clear, that's less clear, or at least I don't see it clear now. But I think it's a good idea. I would suggest them.
Yeah, thanks, and sorry for asking so many questions. But,
no, thank you.
Yeah, I guess that's probably all for today. Let's thank Martin again. Thanks for the very nice talk, and I'm now going to stop the recording.